Started. So, all right, tonight we're going to go over kind of the next thing in machine learning. Last week we did linear regression. Tonight we're going to flip it and do logistic regression. And we'll talk about how that's different. Okay, so first, just kind of overall what we're going to do tonight. Just a couple things, logistics. I think we kind of got started already with logistics with where everybody's from. We're going to review more homework. We are then going to get into logistic regression, which is a statistical model. You really have either statistical models or you have biological models, which would be neural networks. So most of everything that we'll be going over will be statistical models. So with the logistic regression, we're going to go through the development of the model from scratch and then do the Python implementation, both from scratch and then with the models that come put together already. And then what we're going to do is we're going to go into the evaluation of the classification models. You know, how do we tell whether we did a good job or not, whether it's a good good model, which we'll talk about accuracy, precision, recall, F1 score, and then the ROC curve, the ROC curve, and AUC, the area under that curve. Then we'll talk about the homework for tonight. Okay, so just some generic stuff. There's my email address, phone number. If you have any questions, please reach out. There I am on LinkedIn. deepersideoflearning.com is my website where I post all of the lectures. Then there's my GitHub, which is Deeper Side of Learning, and then within that, the lectures folder. Okay, so let's go over some more of the homework. We went over some of it last week, and we'll talk about some more of it this week. So first we'll look at Mandar's homework. Okay, and as always, please ask me any questions, interrupt me anytime with any questions. So, all right. So remember, this homework was to take the IRIS dataset, the bunch of different models that I did in that first demo, and expand on it. You know, do several things. You know, whatever. There are a whole bunch of different possible things you could do. So let's see what we did here. Everything so far is pretty much the same as what I did. Okay, here's a different type of plot. Scatter plots with colors. Okay, so basically you're coloring the different the Viridalis. Okay, so I guess the different types you did different colors, and wherever they overlapped, that's the that's where the color is really changing. Okay. All right, so yeah, this is looking at sepal length versus sepal width and the different types. And okay, then also, you know, another one, but this is petal width versus petal length versus sepal width and sepal length, and it's much easier to see the different groupings this way. Okay. All right, so all the different models. Okay, this is basically the same, the graphics. Okay. All right, so basically that was the main thing that you did extra, which was some other graphs, some scatter plots with colors. Okay, I mean this was pretty much open ended, so you know whatever you saw might make sense to add. So all right, let's look at GitHub at Selena's. Okay, so jumping in. Okay, so looking at null data, if there's any null data, check if the data is clean. Okay, that's not something I did, but looks like everything is good there. Okay, some averages. Okay, this is not something I did. That's good. More EDA, more analysis of the data. You know, see what it's like. Okay, standard average and then standard deviation. How much does everything change? That's good. Okay, here's the regular stuff. Histograms, scatter plots. Okay, here's a different type of scatter plot. This is joint plot, which has got distribution. Oops, sorry, distribution going across the top and across the side, and then the scatter plots in the middle, which that's nice. And then here's a scatter plot with different colors. So now we're seeing how this breaks out. And this is actually a good plot because we're going to see this again in a little bit. This is looking at how we can separate this data. We can separate the iris setosa off very easily than separating, let's say, the versicolor from the other ones, or the virginica, because there's a lot of overlap. They're more similar. And again, we can see the same kind of thing here. We're going to look at, we're also going to do the iris data set tonight as well. Okay, so here's creating models, then that same group. Okay, now we're tuning the k nearest neighbors. So change the range. For mine, I guess you know, I had a much smaller grouping. So you're having it go from 1 to 20. So that's good. So we can see which is more accurate. So we had a bump here, way out there, but originally it's just the first couple of groupings that, you know, k values that have the highest. Okay, so now okay, we're still working the k neighbors classifier. Okay, just all right. So looking at okay, so now we're doing from range 1 to 10. K neighbor. Okay. So half of the, you know, the best results that you're going to get are stuff that's really readable. It just jumps out. So okay, so we're tuning the SVM hyperparameters. Okay, different kernel types: linear, poly, RBF, sigmoid, pre-computed. So you're trying the different ones, and it looks like RBF. Oh no, the linear is the best one, which is interesting. So you add some complexity to your model, and you actually get a worse answer. Okay, so then we're now doing the XG. Oh, did you get the XG boost? Okay, there were issues here, so we should really sit down and review these, which we will go over these model types later, just not right now. Okay, and Monique, I apologize, but you go over some stuff that we talk about tonight. So I really, I'm going to go over yours next week. Okay, so Ranjiv, here's the latest edition. Okay, okay, so you do some different colored plots, all the different the seaboard, the pair plots, looking at each versus each feature against every other feature. And for some reason, yeah, this I could not quite get why you have the red, why you had different colors in it. then I realized that your data set has got missing data, which mine did not. So, but this is good that you're working on something with missing data, because that's very important. We got to do the cleansing. So yeah, I'm not sure where you got your data from, but you also have some weird classes out here like Versacolor versus Iris Versacolor, or Setosa spelled incorrectly. So that was your different colors in here where your data is messed up. So I'm not sure if you went in and changed your data, or you got data from somewhere that had bad data in it. So there's some cleanup of data. Looks like you cleaned it up. That's very nice. Somewhere I think you got rid of the null rows. So you're looking at averages and or the different, just a few examples of each of the types. Okay, so here's where you got rid of some rows. Okay, so you have a clean data, a clean data set that you wrote to CSV. Okay, that's good. Okay, and then now I don't see all the other colors. It's very clean. Okay, now you do these violin plots, which I think are very cool. So you're looking at the distribution of the sepal length whenever you look at the different types. Standard, the average, and the standard distribution, the full range. So that's nice. You can get an idea of, for each of the different types, how much they vary and what type of variation each of the features do. Okay, so now we're looking at different types, different models. Okay. Okay, so now, and then you evaluate each model separately. Okay, so that's all very accurate in SVM. Okay, that one has different accuracies. So you're trying different variations of the models. So that's good. That's good. All right, so that's the homework. And I'm a little perplexed. You guys are not turning in. You're not really doing a lot of the homework. Getting behind. We need to figure out, what might be happening. Definitely reach out to me if you're having some issues with keeping up. But yeah, there's a lot to do. I do understand, and if you're having a problem coming up with some of the answers, just let me know. I did make the homework, not incredibly easy. But yeah, I made it a good challenge for you guys. But you're up for the challenge, and this data science, sitting in class, learning all of this is very, very important. However, doing it is what is going to get you there. So that's where going through this homework is very valuable. Kyle kind of talked to me and said, that's what your students are really going to get out of this class, is when they go do this stuff themselves. I'm like, oh, okay, well, we got to get them to do that. So I'm going to talk to him about that, and see what we can do to get you guys jumping in there and tearing apart these data sets. Just reach out to me. I'm always available. So, all right. So let's get on to what we're going to talk about tonight. You can see that there's a lot of different types here, a lot of different algorithms. I broke it down to classification versus regression. We went over regression last week, the first one, which is the linear regression. tonight we're going to go over the first classification algorithm, which is very, very similar to a regression algorithm. If you remember, that was, if you have continuous variables for your output, then you use the linear regression algorithm. If you have distinct outputs, yes or no, is it this type or that type? Then you use a classification algorithm, and that's what we're going to talk about tonight. So we're going to go into logistic regression first. And first we're going to talk about the data, what types of data do we use logistic regression for. Then we're going to go into that model, that logistic regression model, down to the lowest level. We're going to build the math up from scratch, which doesn't take long and it's not overly complicated, so don't get scared. I'm going to do a little bit of hand waving when it comes to the gradient descent, because the math can be extremely complicated. And then we're going to jump into Python and do the coded example, do the handwritten example that we developed up here, and then we're going to use scikit-learn, their model library, to perhaps do a much better job at getting the answer. It'll be definitely much faster. We're doing it with the basic math, where their libraries have really made it much more efficient, and can so it ends up being just a lot faster, and you will definitely see that. Okay, then what we're going to do is evaluate our classifiers. We're going to see if we're doing the classification correctly, whether we're doing it good enough for what we need, which is kind of our usefulness. What's our accuracy of our output? We're going to break that accuracy down into different types: precision, recall, and then the F1 score, which is a combination of both. Then we're going to look at the ROC curve, which will give us an idea of, not necessarily how accurate, but how much did we really break apart our data set? How much did we really classify our data? Did we come up with two distinct classes, or is it really just random the way we did our classification? Was there enough information in our input in order to get a good output? Okay, so let's jump in. Okay, let's talk about classification. The basic, very first type of classification is just, is it a blank? Is it a mouse? Is it a spam? Is it a cat or not? Stuff like that. Are we just, the answer to the question is just a yes or no, and we will evaluate that to either a 1 or 0. That's the first level, which is what we're going to do tonight. But it's easily extended to multinomial, which now we're going to break our output, our goal, into a bunch of classes. Is it this, or this? And one of those will end up being the right answer, not just, there won't be just one that's either yes or no. We can have several be yes or no. And only one of them will be yes, because whatever we're trying to classify can't be two things at once. So a good example of this would be our iris data set. Is it versicolor? Is it setosa? Is it The other one, I forget what the other one was. So so yeah, that's a multinomial classification algorithm. And another example of this is very similar to multinomial, just kind of stated in a little bit different way, which, if we have a set of integer numbers that we're trying to guess, like how many, I don't know, how many are there in that picture? How many people are there in the picture? Then we're actually going to do an ordinal is what it's called. And it's going to be very much like a multinomial, very much like a binary, just multiple binaries. It'll be, is it a 1? Yes or no. Is it a 2? Yes or no. Is it a 3? Yes or no. So we'll just have multiple outputs. Each one of them will be either 1 or 0. Okay, so all right, so logistic regression. Logistic regression is very, very similar to neural network, one neuron of a neural network. It's actually not any different. Last week we did linear regression and we showed that it was also very similar to a neural network with a very simple linear activation. That was just a straight line. This time we're giving it a soft step or sigmoid activation. This is the function that we're feeding our inputs, our sum inputs into here, and then we're feeding that into the sigmoid function, this function, in order to have an output. So basically, if our output is over a certain size, if our summed value is over a certain size, then we'll get a 1 for the output. If it's less than a certain size, then we'll get 0. And this one shows -1, but the one we're going to pick is 0. So it's the weighted sum of our inputs. Really no difference. So here we're showing all these weights, and then multiplied by our inputs, and we have this bias in here. We're always going to have this 1, which feeds into the 0th weight. And then once we have the weighted sum, feed it through the function, the activation function. So this is our logistic regression. It's very simple. It's a very simple model. One perceptron, one neuron. So just to show it differently, well, actually, I'm showing again the activation function here because we need to look at this loss function more closely. So this is what our output will be of our network, and we'll either be training on a 1 or a 0. So our error, the way we did in the previous, when we did neural networks, all we did was just subtract the 1 from the value, from the output, and that's our error, and that's our loss. However, we're using a different kind of loss. In this case, and it's a more efficient way of doing it. Gives us a very, very simple answer. And I'm going to develop this loss function now in the next couple of slides. So that's what we're going to try to minimize, is this loss function. Okay, so a very easy way to come up with a loss function, our losses, our difference between the output and what we want it to be is going to be between 1 and 0. So what we want is for that to be smooth, so that when we take that partial derivative that we talked about before, we can easily go down. So what we do is we picked a log function. A log function looks like this, the log of an input. So we're going to cut it off and use just this part of the log function. And note, okay, that this is somewhat arbitrary how we develop our log function, our loss function. We're looking for certain properties of that loss function that we can easily optimize, we can easily minimize. So this is what somebody came up with, and now I'm kind of giving you the development of how it works. Okay, so what we're going to do is we're going to take one part of this log function, just this part that's between 0 and 1, and we're going to flip it, make it negative. So again, we're going to call that h, and it's h theta, because in this particular development, the weights, they're putting into a vector theta. So h is a function of those weights, and it's a function of the input. So going back to our here, we sum all these up and pass it in. The output is a function of the weights, and which is theta, and all the inputs. So that's why there's giving you this. So we're going to take this one part of the log, we're taking the negative of it. And we're also taking another part. If we say log of 1 minus x, or I'm sorry, 1 minus the log, that just flips it around. And what we're going to do is we're going to say, if our output is 1, use this value. You use this function for our loss function. If our output is 0, then use this function for our loss. So that's why, this is what our function actually ends up being. It's if y equals 1, we're using that negative log of h theta of x. And if y equals 0, we're using the negative log of 1 minus. Then what we're going to do is we're going to add these two together. So here was the first part, okay? And we're multiplying it by y. So the first part was if y equals 1. So if y equals 1, then multiplying it does not change this value. So that's why we're multiplying it. It also makes, if y equals 0, it makes this side equal to 0. Then we're going to say this other part, this down here, we're going to put it and multiply it by 1 minus y sub I. Now this one, if y equals 1, which we should be getting this, 1 minus 1 is 0, so this will cancel out. And if y is 0, which is when we want to use this function, then it's 1 minus 0. So it just passes this side through, not this side. So for all of the inputs, we are, I'm sorry, not all of the inputs, all of our training data, we're going to add it all up and then take the average. And for some reason, and then we're going to do a negative because we took the negative log of x on all of them. And here's the negative log of 1 minus h. Sorry, h, not x. All right, so that's why we have the minus out here. And this can be rewritten as a as a bunch of vectors multiplied out like this. So h is a vector, y is a vector. You have to transpose them in order to be able to multiply them. And then, I mean, basically it ends up, you end up adding all of them up and then dividing by n. This is called either cross-entropy loss or log loss. That's what this type of loss is named. It's much more complicated, perhaps, than the sum squared errors loss, which is what we did last week, and what we did with the neural network. But it ends up being quite simple when you calculate the gradient, which with the gradient, what we're trying to do is, like last week, we're trying to see how much the weights should change if we want the error to go down. And that's how you define a gradient. So if we take the derivative of this with respect to theta, or derivative of j with respect to theta, and remember h is x0, x theta, which is, if we go back, we multiply all these times the w's, that gives us our x theta. And then we're passing it through a g, which g was our activation function. So that's what h is. So I just plugged h in here. So it's just x transpose of times h minus y and divided by m. So that's how we get our gradient. And with some calculus, we can show that if we want to take the gradient of this with respect to theta, this is what we get. That's my hand waving part of this exercise. Okay, so now we have this calculation, we can then go and actually develop this in Python. And if you guys want to, I'll go ahead and I'll copy this into Zoom so that you guys can follow along with me. So it's all in my GitHub. I will copy it over there anyway. All right. So I guess any questions so far before we jump into the coding part of this exercise? Okay, so Monique, nope, I like it. All right. Let me find my, this was dinner. My code, here we go. Okay, so we're gonna create a new one because I'm gonna create this from scratch. All right, let's see here. I move the windows around on my screen. All right. All right, so the first thing that we need to do is grab our libraries. Got them all packaged up here, nice and neat. Okay, so while that's going, let's see what's next. Okay, so what I do next in my code is define a bunch of functions. But we're gonna go past that for now and come back as we need these functions and load them in. So the first thing we're gonna do is load our data set. Okay, library is still loading. My computer is not fast. Come on. Okay, so let's look at what's next after this. Okay, that's almost there. Okay, so if you look here, I'm going to do a much simpler dive into this data set than we did last week even. I am I load the iris data set, and then what I do is I pull for X, I pull only the first two columns instead of all four columns and predict Y. I'm only predicting Y based on two of the columns, not four. And then also, I am only going to predict whether it is the first class or not. And the first class, I forget which one it is, but it's the smaller class. Okay, so, all right, got a question here. Do we have to be good at these formulas, or can be referenced while working on the coding part? Just referenced. Yeah, you don't have to. You have to kind of know how it was developed. Nothing more than what we talked about tonight. It's interesting because there was a question in Slack for the data science dream job. There was a comment from somebody, I forget who it was, but they said they were in an interview, and some of the interview questions revolved around logistic regression, and could they explain how logistic regression was developed? What's the math behind it? Can they just talk about it, talk it through? So if you understand, what we went through tonight, just from how do you develop these algorithms, then you would do fine. But so many times all you do is just see, okay, I'm going to use a logistic regression model and here in fit, and you're done. That's what you see in all of the applications. But so this gives you an idea of how it was developed, how it came about from scratch. So it's definitely good to know that. Okay, so so what we did was the iris target, we said if it's not equal to 0, then multiple, if it's not equal to 0, that's one value. And if it is 0, that's the other class. So this is just a binary class, 0 or 1. And we can see what these look like. I always like doing this. So X is just all your data set. It's either, it's two columns, first two columns. And then Y is 0 or 1. The first few are one type and the rest of them are the other. Are the other two types. It's clumping the other two types into one, the larger types. Okay, so what are we doing next? Okay, so now I created a function to scatter plot, do a scatter plot. So if I go up here, and if I can just define this basically now, I'll define the function, and then I can run it. Back down, the scatter plot. This is what I would look like, and I've got two different colors here, and I'm plotting X, one X against the other X. And what I did was I said all the blues are one class and the reds are the other class. So I've got like the sepal width versus a sepal length or something like that. The first two columns, whatever that is in the iris data set. So you can see this is pretty easily separatable. If I draw a line down the middle here and say everything that has, sepal length of 4.8 and a sepal width of 3 point whatever, everything that's in that group, make it, then I know what it is. So if we can end up drawing a line down the middle here to separate these two classes, then we would be right on. So let's work to do that. Okay, so now we're going to create our model, which I've got this logistic regression hand class that I created up above. So let's run that, and then we're gonna talk about how all this works. Okay, so I just defined my class. So this is some parts of Python that you guys have to be familiar with. You have to be good at is creating classes, and then you define methods within your classes and properties of your class. Anything self dot, that's a variable, that's a property of your class. So when you instantiate a class, create a variable that has this class as its type, it runs this formula or this method, the init. And anytime you have an underscore as part of the method name, that means that this function is only useful within this class. Cannot call it from the outside. It's a local function. It's not global. It's not accessible anywhere but within this method, within this class. So this init method defines what your variables are that you're passing into your class, and you just always put self. And I'm passing in x, my x variable, my input. I'm passing in this LR, which is a function. It's a hyperparameter of logistic regression, which is the learning rate. How fast is this going to learn? How much of that gradient am I going to move every time? How many iterations am I going to use when I train this? 100 iterations is the default, and this 0.01 is the default. I can when I create this class, an iteration of this class, instantiation of this class, I can give it different values. These are just the defaults. Okay, this fit intercept, is when I create this logistic regression, am I going to have that bias term? Am I going to have an intercept? Is it going to be mx plus b coming in before going through the activation function, or is it just going to be mx? Is it going to go through 0? So by default is true. And I have this verbose, which we'll see how that's used later on. Okay, so first thing I do is I just set all these variables to what I passed in. And I do a couple of things. I'm adding. I'm actually, if I pass in fit intercept, then I run this method, internal method, add intercept to x, which is right here. What I do is I create an intercept which has a bunch of ones, and the number of ones that it has is the length of x. So I end up adding a column of ones to x is what I'm doing here. Concatenating x with that column of ones that I created with the intercept. So that's what this, if I've got to intercept, then I've got to expand x by one column with all ones. Okay, and then I set my initial weights to zeros. I'm creating that variable here, theta. Okay, so here's add intercept. It's an internal method. Then there's a sigmoid, which is just a function returning the 1/1 plus exponent of minus whatever I passed in. And then I have a loss function, which is that formula that we came up with for the loss, which we will need it in our fit function down here, which is the next thing. Okay, so so fit passes in x and y. Now see, fit doesn't have the underscores. It's the first function that I can access from the outside. and we'll get back to this in a second. But this is how we do our gradient descent. Okay, then I've got this predict probability function. Okay. This gives us back, if we go look at our, hold on a second. Go back, look at our, this gives us this variable that comes out of our summation. All right, so basically it's a dot product of W of our weights times theta. And then we have our predict function, which what we do is we take the output of our function here and our input to the activation, and we just round it. Is that really correct? Because we're not passing this to the activation function. Oh, that's interesting. I think I found a bug in this. Should be passing it through the activation function, then rounding. I have to look at this. Oh no, I'm sorry. Never mind. There's a sigmoid here. We take the sigmoid of, okay. So this, all right. So this is the output of the activation function, and the output of the activation function, what we do is we say if it's above 0.5, then the output, then we're looking at one particular variable, one particular class. If it's less than 0.5, some level, then it's the other class. So yeah, and that's what this round is. Basically takes anything above 0.5 and says it's a 1, anything below 0.5 and says it's a 0. That's our threshold. Okay, so we defined our logistic regression, our class. Now, let's go back. Well, let's run it. Okay, so the first thing is create it. Create the function, create the model. Instantiate the logistic regression. Okay, and then I said, actually, you know what? I said verbose equals false. I'm going to change that. Back up here and say verbose equals true, so that I can see what's going on inside. As we do the next function, which is fit. Okay, so you can see it running, and since it's verbose, what it's doing is giving us the loss every 10,000 steps. So now let's look at the fit function inside here. This is where we're doing our gradient descent. First of all, since we're passing in x again here, we need to add the intercept, add the extra 1. Then the number of iterations, whatever number of iterations we passed in to the variable. In here, we said 100,000. In our instantiation, we said, I want more, I want 300,000. So we're going to go through our iteration that many times. So the first thing is to get a z value, which is a dot product, which is the weighted sum dot product of the x times our weights. Then we're going to pass the answer to that z through our sigmoid function. So this is our feed forward process. Okay, then we need to calculate our gradient, which came from that function x dot product of h minus y, and divided by the r, which is the size of our data set. How many rows are a data set? That gives us our gradient. Then we're going to change our theta, our weights. We're going to subtract the learning rate times the gradient. That's pretty straightforward as far as the process. Some other stuff they do here. Let's see. Afterwards, okay, then now they're calculating the loss. Okay, this is where the loss is needed. They're just, in order for us to show print the loss, if we're doing verbose, we need to calculate it. So once we modified our weights, we then feed forward again. So z moving forward, and then take the sigmoid of z to get h. That's our final output. And then with that, we subtract from y. We put it through this loss function up here, which is that log loss. And then we print that if verbose equals true, and we're going through the 10,000th next iteration. We do a mod function on I. Which iteration are we in? And at 0, then we print the loss. So that's how our fit works. I let it run while we were off. It took 25 seconds to run this. As you can see, our loss is going down. So that's good, and it could have gone down further. We could have run this for even further. But went ahead and just let it go for the 30,000. All right, so now that we're done, now that we have a model, a trained model, let's look at some stuff in it. Okay, I'm skipping over some stuff here. Let's get what the accuracy is of our final model. Our accuracy is perfect. So the way I got that was I said, okay, take the model and do a prediction on X and put that in a variable called predicts. And then I took the average of this, added up all of the times where it was right, where prediction equals yes. That gives us a 1. So I took the average of that, and I got a 1. Now theta is our weights. So these are the weights that it ended up with: minus 25, 12, and minus 13. There were 3 weights in there that we needed. There was 1 for the bias, 1 for x1, and 1 for x2. So, okay, then let's see what it looks like now with this value. Now I've run this other function, plot with line. Okay, and I haven't defined that. So let's go up and grab that. Before I plotted, just did a scatter plot. Now I'm doing another type of plot, but very similar. You'll notice that the first part of this is exactly the same. I'm doing a scatter plot. I need to run it. And then I plotted a line in the middle. And this is a kind of an ugly way of doing that, but it's the example I grabbed. So let me pull that up, run this. Too far. Oh, still in definitions. Plot with line. Okay, so now I've got the scatter plot plus a line down the middle, and it 100% was able to divide it up. So Awesome. Yeah, that's why I got an accuracy. Hold on. Can I go up? An accuracy of 1.0. Perfect score. All right. So let's see what we're doing next. Okay, now there's a couple things that I'm skipping because these are the next parts of this lecture, which is the cross. My mind just went blank. We'll get to that. The rock plot. Okay, so some other things. We will get to that. Different ways of. Right now, we'll just stick with accuracy as being how well our model worked. So now, what we're going to do is we're going to see another version of this, a little bit different version, one where we're picking a different iris set to do a prediction on, different iris type. This is now I'm saying if the target is not equal to 1, then oh, this is just all other types. Hold on a second. Okay, this is not equal 0. Okay, so if it's not equal 0, it gives us a 1. Okay, so it's either 0 or 1. This is predicting one of the other values. And then this is what our measurements look like, for that other class. So now you can see this is not completely separable. We can't come up with a perfect answer for this one. So we're just going to have to pick the best guess. Whichever line separates the most of them. That's what we're going to try to do. But we're going to do it in exactly the same way. We're going to create we're going to instantiate the model. And this time I'm going to leave verbose equals false, the default. Just let it run. Hopefully it'll take less than 30 seconds. The last one took about 30 seconds. So let's see what we're going to do next. Okay, then what we're going to do is show what the accuracy is, and then what the final value is, the final line. What are the parameters? Okay, so our accuracy this time, we were only able to get 71%, not the whole, not everything being perfect. Now let's see what the line looks like once when we plot this. So this is the best line that we could do. We basically got as many reds on that side with a few reds on this side, as many blues on this side, there's hue on that side. This was the most accurate one that we could come up with running it 30,000 times, 300,000 iterations. So that's using our model. Let's now go and use a standard model, the scikit-learn model. It's very, very similar. I created my model instantiation very similar to how scikit-learn does it. They've got this one parameter c equals 1e20. Not sure what that is. I did not look it up. That's the one thing that they one hyperparameter that we passed in. That was fast, 22.9 milliseconds. And it showed me what all the standard hyperparameters are that came in to this, that passed into the logistic regression. That's how that model works. So now we're going to look at the score. Okay, so what is this? So now there's there's this thing called score, a formula called score, method called score that they have that we didn't create in ours. We could have created this. We could have put the accuracy inside our class and had that as the method for our class. We didn't, so but this one did. Scikit-learn, they added it. So what I'm going to do is just run that, pass in X and Y and say, okay, what score did I get? Then I'm going to do the same thing I did for our value, our model. I'm going to find out what the predictions are, and then I'm going to calculate the accuracy the same way. And then I'm going to print what the model coefficients are. Just kind of lump them all together here. Their score is the same as our accuracy, so we're both doing it right the same way. And then here's what the model parameters are that they came up with, which it's -8, -0.14, 3.2. If we go back up, that was the same as we got for our parameters, -8, 0.14, and 3.2. So it's a little different. Actually, it's 3.2. It's exactly the same. So, all right. Okay, so there's some more stuff that I'm doing that we will get to. Okay, then a ROC curve, doing that, that's next. Okay, then what I do is I'm going to redefine to that original data set that we started with. I'm going to change my y's back to either the first class or not. Okay, and then I'm going to train using the scikit-learn's instantiation and see, okay, and now we got an accuracy of 1, exactly 1. Okay, and I didn't plot this one, but you can imagine it will look exactly like this, with a line down the middle. All right, so that's it for how logistic regression works, both from, we created a model from scratch, just using NumPy, with math, and, with vectors and some derivatives. And then we said, okay, scikit-learn, somebody else has already done it, let's just use theirs. And came up with exactly the same results. So let's go back to the lecture. So that was the Python coded example. All right, so now let's talk about the other parts of, well, the classification of models in general, okay? Not just logistic regression, that's a basic one, but classification of models in general. How do we tell if we did a good job? There's that accuracy, okay, which we measured. How many did we get right? Okay, but there's other ones also. And what I'm going to do here is kind of develop those those values, and then we will talk about why to do this. Why does it make sense? What is recall and precision? So in order to do this, what we want to do is create this what's called a confusion matrix. Okay, and so let's break this down. It's what we need to do is fill out this little graph, and if it's multiple classifications, then your confusion matrix will be larger. But so we have two columns here. Our actual is either positive or negative, right? It's either 0 or 1. It's either the iris setosa or not, okay? So if it is, if our actual is that, then we want to fill in this column. If it's not, if it's a negative, then we'll, I'm sorry, if it is a positive, we'll fill in this column. If it's a negative, we'll fill in this column. Okay, so then there's, okay, what did we predict? Did we actually predict it to be a positive, if it was a positive? Then if we predicted a positive, then it would be in this column. If we predicted a 1, if we predicted a no, a 0, then we would fill in this row, sorry, not column. So now what do each of these quadrants mean? If it ended up in this one, that means that the actual was a positive and the predicted is a positive. So that means it's a true positive. True means I got it right. So you would add 1 to this column, or this block, this quadrant. If it was actually not that, it was a negative, then, and you predicted a negative, then you'd put it into this cell. And also, let's look at the other ones. If the actual was a negative, but we said it was a positive, that's a false positive. We were wrong. And if the actual was a positive and we predicted that it wasn't, then we put into this. So just real quick, well, we'll get to that shortly. All right, so now there's, so from this grid, we can calculate our accuracy. We take the middle column, or middle diagonal, true positive, true negative, add them together, and divide by all of our other grids, our total number of guesses for actuals, our total number of data, our total data set, to count for the data set. That gives us our accuracy. So now we have two other things which we're going to define as recall percent and precision percent. Okay, recall is how many positives, so actual positives, did we identify correctly? It would be this one, just take this column right here, where the actual positives, and figure out how many, what percentage of them we got right. That's our recall. That's a way to judge how well we did it. In other words, we don't care about all the negatives. We just care about the positives. And then there's another one, which is precision. So out of our predicted positives, how many of those were correct? Okay, that's a precision percentage. So it's this true positive divided by true positive plus false positive. Now, each one of these by itself isn't the best answer. Sometimes what we want to do is combine them and give us an F1 score, which is take the recall times precision times 2 and divide by the recall plus precision. So it's a way of combining those two measurements to give us a final number, because one isn't necessarily most important. All right, so now that I defined everything, what do we care about all of that? Let's give an example. Let's say that we're developing a cancer screening. Our situation is we've got 1,000 patients that we tested. 5 of them actually had cancer. So the goal is to, based on a bunch of features, a bunch of variables, a bunch of measurements that we did on them, questionnaire, whatever, to be able to predict that. So now let's say we created this model. We came up, with our predictions, and we predicted that there were 7 that had cancer. 3 of those 7 were 7 that actually had cancer, and 4 of them we got wrong. Now, is this okay? Is this accurate? It's pretty accurate. If we calculated the accuracy, we got 3 plus 991 correct, divided by 1,000, we get 99.4% accuracy. That sounds really accurate. However, let's say this was a screening where we're just testing, everybody when they come in, their first, their first time they come in, we're giving them these tests. We're trying to figure out. So 2 of them had cancer. Okay, we're good. We're developing cancer. Didn't know about it. Went home thinking I don't have it because we told them that they don't have it. That's not good. As far as the 4, we said, okay, yeah, they actually have it, or we said, yeah, they probably have it, but they don't have it. It's a scare for them. Okay, we're going to say, we need to come back in and take more tests. And then once they take more tests, then we'll show, yeah, you actually don't have it. Sorry, you seem to be at risk. That's okay. But this false negative is a big, problem. So if we look at the recall, okay, which is 3 over 3 plus 2, 60%. 3 over 5, that's 60%. That's just too low. We would want to do something to get that up. Now, it may go at the expense of precision, okay? Because let's say to get that up to 100%, we said, everybody that comes in, you have cancer. We got that up to 100%, didn't we? That isn't good either, because now we're scaring everybody. If we did that, then that means that we didn't say anybody was negative, okay? And our precision, which would be 3 over 3 plus 0, or actually 5 over 3 plus 0, would be 0%. So our precision is just way down. That isn't that great either. That's just, we really want to balance these two. But I think we want to balance on the error of recall. We want to get that up without neglecting our precision too badly. So let's say somehow we modified our model to catch more, to say more, be more liberal with our saying that possibly they do have it. And there's a way we can do that. The way we can do that is change our threshold. Okay, when we pass our aggregated sum through our activation function, we're coming up with point something, right? 0.6, 0.7, 0.8. What we initially said was that if it's greater than 0.5, it's a 1. It's a yes. They've got cancer. Now, why don't we change that to bring it down a little bit? Let's say if it's greater than 0.3, then we're going to get a different model. We're going to get a different output. It's not going to be that much different, but it will be more. It will be. It'll catch more. It'll be more apt to say they have cancer. So let's say we did that, and we just all we have to do is just change one value in there, and then run our model through again. We don't have to retrain the model or anything. Let's say we came up with this. We lowered that enough so that the false negatives, we got 0. So what we said was, okay, it's accurate enough, or we're making it a little more sensitive. In other words, if you're showing a little more of whatever it is we're looking for, then we're going to say you have it instead of just it has to be all the way up to 0.5. So what ended up happening was we then said there was many more have it, okay, and more false positives. We'll be more apt to say that you have it. We're going to catch some that actually don't have it. So our precision went down, our recall went up, our accuracy went down, from 99.4% to 99%. Advanced one score, we noticed from before it was 50%. It's now still 50%. It did not change. So that's just somewhat of a coincidence. But looks like I had my, okay. All right, Monique has a question. Tuning the model for either high precision or recall. Okay, the hyperparameter of logistic, which is C. Okay, the threshold is is the only thing that I'm using to fine tune the precision or recall, not the C value. That's all in my particular example here. This is the typical way, and you'll see shortly why this is what I did, why I changed the threshold. That's a big, easy way to do this, and there's a lot of other advantages or ways we can measure our model using this. Okay, so all right, so that was one set of measurements, and you kind of can see how recall and precision play off each other. You increase one, you decrease the other by changing your threshold. So now there's this ROC curve, okay, which, sorry about that, I've got a typo here. Give me a second, let me fix that. Okay, and go back to, okay. So in our ROC curve, it's called the receiving operating characteristic. Receiving operating characteristic. I'm not sure why it's called that, but that's the technical name. What you do for this curve is you take the true positive rate, you put it on the y-axis, and you put the false positive rate on the x-axis. And then you do a scatter plot, or a line plot, connect the lines. And so the true positive rate is, the true positives plus false negatives. It was the same, as the recall. And then the false positive rate is the false positives over the false positives plus true negatives. So basically what you do is you compare, okay, how accurate was I was on the positives, how accurate was I on the negatives, and you plot that. And here's the different ways to calculate it. And then there's this area under the curve, which basically and we're going to show this on the next slide, that if you end up with a straight line across the middle, or even on the bottom side, then your model didn't tell you anything. It was just like random. It's like it's untrained, okay? So if the area under the curve is less than 0.5, if it's either flat or going down, then you end up with bad predictions. If you end up on this side, if the area under the curve is on this side, if the curve goes up on this side, then your area under the curve is between 0.5 and 1. So the higher the better. The more this curve approaches all the way up to this corner, the better. Now, remember we had a trade-off between recall and precision. You also have a trade-off here between the true positive rate and the false positive rate. If you have 100% on one of them, then the other one will be 0. And you can, I'm sorry, if you have 100% on one, then you have 100% on the other. Same with on the other side. So that's how you draw this curve. So okay, so here's an example of completely 100% guessing. I didn't have any idea based on my model whether it was positive or negative. So if my actual is 500 positives, 500 negatives, just to give an example. And I guessed exactly somewhere in between, half and half. If I plot that, I got 50% on both. That's if I have a threshold, and what you do is you vary the threshold to go from one end to the other. I got 50% here right in the middle, 50% by 50%. And if I had a threshold of 0.3, ended up with 30% and 30%. Okay, here's my threshold of 0.3. If I had a threshold of 0.3, then my model would guess true positives to be, less of the time, 100%, 150 of the time, and then, or it would guess positive 150 times, 150 at a time, 150 out of 500 times, and negative also 150 at a time. So I really don't. This model gives me no information whatsoever. If I have, like, for instance, my model where I was, somewhat close, if I had a 0.5, if I measured these things, I ended up with the true positive rate of 60%, 3 out of 5, and a false positive rate of 0.4%. So that ends up being, this spot right here. If I lowered my threshold to 0.3, then my true positive rate went all the way to 100. My false positive rate went up to 0.1, so I went over a little bit. So you can see this is a pretty good. I have a lot of meaning, in this model. I'm able to do some pretty good predictions. Right, and yeah, the 0.3 gave me this one. This is where if I had a threshold of 0.3. And just the way you get this graph is you just vary this predicted threshold from 0 all the way, or, I'm sorry, 0 at this side all the way down to 1. So that gives you the ROC curve, and as you can see, this kind of curve has very large area under the curve. I estimated around 0.99. All right. So the next thing, is looking at these evaluation methods in Python. So let's go through that. All right, so if we go back to our so now what I'm going to do is actually just run everything and show you as we go through. That'll be much quicker than recalculating than copying and pasting. All right, so I am defining all of my classes and functions here. Okay, and I'm going to go ahead and just define it. We'll go up and explain it when I get there. Okay, so now I'm pulling in my data set. Here's what my first data set looks like. Okay, I'm calculating my linear logistic regression model. Okay, it is moving along. Takes 10 to 15 seconds. Okay, and I'm going to skip this part. We'll come back to that. Okay, it took 23 seconds, which I'm not sure how this does 23 seconds. That wasn't 23 seconds, but whatever. It says wall time. Okay, so here's plotting with the line. So now I have my answer. Now what I'm going to do is confusion matrix. This is a very, very simple, well, it's actually two confusion matrix. And it's a function, so let me go up and break down my function. Print CM. Now, confusion matrix is a function you can pull in from scikit-learn. It's in the metrics, it's part of metrics. And what you do is you feed in all of your actuals, your y's, and all your predictions. And it gives you a matrix, and I'm printing that matrix. So we go back down, I'll show you what, that's this matrix. So what it is 50 were actually that first variable, or that first class. 100 were not that first class, and I guessed everything right. This was the 50 on one side, this is the 100 on the other side. I didn't get any false positives or false negatives. Now, there's that's not a very pretty confusion matrix. There's actually a better one. And it's called confusion matrix, and you also you pass in the y and predictions, the actuals and the predictions. And here I did normalize equals true, which changes the colors a little bit. But this is what that confusion matrix looks like, just a little bit nicer. Doesn't give you the counts, but gives you a heat map. The darker it is, the higher the number. Okay, so so now what I'm going to do is come up with, okay, this predictions too. In order to do the ROC plot, you need to have the predictions that are probability predictions, not the rounding up to 1 or 0. You need to have the output of that sigmoid. So that's what this predict prob gives you. And if we do that, we see we have a perfect prediction. Perfect ROC curve. It goes all the way up and then over. For every threshold that I pick, I'm given the right answer, except for the threshold of 1. I don't get the right answer. So this is a perfect model. And area under the curve is a full 1.0. Okay, so now I'm going to quickly run through this, redefining the class to try to predict one of the other types, which is in the middle here. It's equal to 0 actually, and 1 if it's not. So it's thinking it was backwards before. Okay, so I am fitting it. Takes a little bit of time because it's my model, a little bit slow. Sorry, we're running a little over here. We're almost done. Okay, so let's just let it run. Okay, so here's my guess, like I had before. And actually, I didn't do the confusion matrix on this one. But I do it when I go down here and run it. I'm just, okay, so here's that sort of good model where I got a 71% accuracy. I've got a confusion matrix here where I got it right 21% of the time, 86% of the time I was also right. So that's where I get my accuracy. But I had some false positives. I had times where I thought it was this particular class of iris, but it wasn't. Or I didn't think it was, but it actually was. So this is what my confusion matrix looks like. So let's plot the ROC curve. We kind of have a curve here. And you notice I did this with ggplot, which is straight out of, it's more of an R function, R plotting characteristic. Let's also, I did it again also with pyplot. And we've got a curve that goes away from the line. It's got meaning to it. It's not perfect, but it's better than not knowing anything about the answer, the thing we're looking for. So here one more time I switched it back to looking at the first set class and ran it through their model And of course, I get the same exact answer, same view. Okay, and okay, one more thing I want to show is, let's say I create this model and don't train it. What does my ROC curve look like? That's what I did here. If I comment out the fit part and I create the model, and then here I have to change this. I forgot to do this because I commented out. Okay, so I don't need this. Oh, it's pretty, it's 2. Is it? No. Hold on. Okay, my ROC curve ends up being right along that line. In other words, my model doesn't know anything about the data that I fed it. Okay, so let's look at the homework. All right, so for the homework, what I want somebody to do is, something I didn't do is have precision recall in F1. So add that to the scores from my data sets. All I did was just do the accuracy, the ROC curve. I didn't calculate the precision recall. So if somebody, if you guys want to do that, that's probably extremely easy one to do. And then expand my model, whether you want to do the creating from scratch, that would be fine. Or if you just want to use the scikit-learn standard model, but expand this to showing the logistic regression on all 3 iris data set, all 3 iris classes. That would be the multinomial and multi-class regression, logistic regression. And also show the precision recall ROC on those. Your confusion matrix will be, larger. It won't just be 2 by 2. Okay, and then if you want to take it even further, do the ordinal classes, or do the MNIST data set, which is the numbers between 0 and 9, being able to tell, the handwritten data set. It's just a simple extension of what we did tonight. And also part of the homework is to take a look at this lesson here, this article, and tell me what's wrong with their ROC curves. There's something pretty blatantly wrong with them. They have a bug, and I don't know why they didn't catch that. But anyway, so there you have it. Exciting stuff. Just, I'm going to hang around for a while. Let me know if you have questions. But yeah, it's exciting going through all of this. All right, so I have a question here. Is the default threshold value for logistic regression always 0.5, or is there a way we can see the current threshold value? Okay, that's a good question. Let me take a look at something. When we ran this, okay, gotta go down. Okay, they gave us what the values are. Let's see if it's in here. Okay, it's not in here. Let me find out about that. You would think that would be one of the hyperparameters. Maybe by default it is Negative. Okay, got another question from Fanny. This is the first class that you've come to. How do you catch up on previous sessions? Watch the videos. I've got, all the videos out there on Slack, also on my website. Best thing to do is go and just, sit through them. It's quite a bit of work, but definitely worth it. I go through just as much information tonight in those other lectures, and it's a great way of getting up to speed on neural networks. And also, just real quick, there's going to be 2 more classes associated with this string of classes, the first 8. Then what I'm going to do is start going into more advanced ideas. I'm going to start looking at things more in depth. There won't be as much like building upon each class as there was these first 8. They're kind of the, get up to speed in data science, get up to speed, on the basic ideas. So the next few classes are going to be going in depth on specific types of models, specific ideas, specific data sets. I'm going to be expanding out from there. So all the stuff that I built on here, we'll be adding a couple of concepts, general concepts, as we expand out to the different types of models. But the stuff that I've gone over so far is just really the basis in 2 more classes of really the basics, the basis for all of these more advanced techniques. So yeah, that's exciting. I'm looking forward to shifting gears a little bit, but yeah, this is all the basic stuff you need.